What if you were marooned on a desert island and there was unlimited paper and pencils, but nothing else, and you wanted to calculate logs? Because, of course, that's one of the first thoughts of marooned people is calculating logs. And you don't have a calculator, no log tables, no slide rule, nothing. Could you do it? Well, we're going to look at a way in this video. So let's look at natural log of 2. And by the way, I recommend for all this stuff that we're going to do, concentrate on natural logs because of the number e. They're more important, arguably, than the common logs, and you can easily convert from a natural log to common log once you have it figured out anyway. So that's what I'm going to be looking at. So you want to calculate natural log of 2. Well, what could you do? Maybe one thing we could do is turn it into an integral. So let's just say natural log of x. How would we turn that into an integral? So you could take the derivative and then the integral of the derivative. So that would be equivalent of natural log of x by the fundamental theorem of calculus. So let's do 1 over, so the derivative would be 1 over x, but I'm going to use a different variable. You'll see why in a minute. And so 1 over t dt. And then we're going to go from 1 to the number that we want to calculate the log of. And, well, actually, I'm just going to keep it generic. But that's what you would do if you were going to find this one. And so if we do this integral, well, then this would end up being natural log of absolute value of x. I'm not going to put the absolute values because it's immaterial to this procedure. And then we would go from 1 to x. And then, sorry, this should have been a t. And then we would do natural log of x minus natural log of 1, which this is just 0. So it would go away anyway. And so that's why we always go from 1 to whatever we're trying to take the log of. So we essentially have the same thing. So this is equivalent to this. But as you can see, we have the same problem because we're trying to find a procedure to take logs, and we need the log. So what could we do? Well, one thing that we could do is use, instead of actually doing this integral, we could do approximation techniques. Well, Simpson's rule says that we can take an integral and approximate it with this expression. So rather than dwell on this expression directly, let's just go ahead and do it. I'm actually going to do natural log of 2 with it. And I do have a video deriving Simpson's rule so you understand it better. I'll put the link in the description. So if we do this, what we're going to end up doing is actually using, this is going to be our f of x. That's going to be this. So it's a lot easier to deal with 1 over a variable. I'm just going to call it 1 over x here because we don't care about the integral scenario here. So we're just thinking of 1 over x. So we can just forget all of this and use Simpson's rule. And so what Simpson's rule says is, okay, basically you think of your function, and that'd be kind of something like that, and you think of your interval, your x interval. We're always going to go from 1, and in this case, since we're taking natural log of 2, so this is what we're doing here, then we need to go up to 2. So it's always from 1 up to whatever number you want to take the natural log of. And basically, it's kind of like doing a Riemann sum. So you're just going to make kind of rectangles. I'm just going to do 4 of them here. You can do more if you want to be more accurate, then do 8 of them or do 16 of them or whatever. But they do need to be n is the number of intervals. N has to be even. And if you watch the video on the derivation, you'll see why you have to use an even number of n's for Simpson's rule to work. But I'm not going to go into that here. So basically, we could divide this up into, or label these. So basically, you just need to identify each x value. And then basically, to do Simpson's rule, you need to take delta x, which is the distance of each of these. So that's going to be 0.25. So here, delta x is 0.25. So we're going to do 0.25 divided by 3. Why do we divide by 3? Well, it's in that video that I'm specifying. And then all we're going to do is figure out the y value of the points. And so we would take, we could call these x0, x1, x2, x3, x4. And so if we plug those into the function, if we take f of 1, well, that's going to be 1 over 1. So it's just going to be 1. So I'm just looking at this now. And then that would be plus, and then it would be 4 times f of the next one. And so that would be 4 times 1 over 1.25. And then it would be plus 2 times 1 over 1.5 plus, and I didn't leave myself enough room, then it would be 4 again over 1.75 plus 1 over 2. And this is something you could totally do by hand. And if you did that, you would get 0.693. You'd be accurate to, I think, 4 decimal places or so. And that's pretty darn good for being on a desert island and having no access to any technology. Notice the formula. The first term has a 1 coefficient. Second one is multiplied by 4, then 2, then 4, then 2, then 4, then 2, all the way to till the last term, which is going to again have a 1 coefficient. So basically, the way it works is you're going to have a 1, then a 4, and then it could be as many of these as you decide to make rectangles for more accuracy. And but it's going to be a 1 and a 4 here, and a 4 and a 1 here. And that's basically how you use Simpson's rule. Okay, so totally by hand, and you could do everything we've done up to now just with paper and pencil, not even a calculator. I'm not saying it's not tedious, because it is. But you could get this on a desert island. What about natural log of 3? Well, so this is where we kind of need to become aware it's not all just peaches and cream. You're going to start at 1 and go up to whatever number that you want to do. But if you only do 4 intervals here, and you try to do like a 10, you're going to start getting off quite a bit. And if you try to do something like 50, it's going to be ridiculously off. So there's things that that's are kind of a downside, but there's an upside because we can overcome all of that. And so I'm going to show you how. Notice that for figuring out natural log of 3, I did 4 intervals here. And so that made my delta x 0.5. I've noticed that anytime you get above 0.25, it's the accuracy is not as good. I personally try to make sure whatever I do, I don't have a delta x over 0.25. So whether that means you have to do more rectangles, which would be a lot more tediousness in your work, or you do other things. And that's what I want to show you is the other things, because you can always add more intervals, the n value. You can always do more of those if you want, but it's a lot of freaking work. So what I did here is, notice when I only did 4 intervals, well, what I got was 1.1, and the actual is 1.0986. So this isn't bad, but I'm going to show you something else I did that gave me a much better approximation, and it wasn't really much more work. It was much less work than it would have been if I had done twice as many intervals. So what you want to do is take the number you're trying to figure out and take natural log of a prime. I recommend primes. We'll talk about that more in a little bit. And so what I did was I just took 3 divided by 2, and that's 1.5. And by log properties, which I won't go into, but you can look them up, natural log of 3 equals natural log of 2 plus natural log of 1.5. And the cool thing is we already have this. So this is 0.6931. And so all I need to do is figure out the natural log of this. Actually, I think I'm going to quit saying natural, because really in higher mathematics, people just start calling this log. Common log, it really isn't as common in higher math. It's definitely there. There's a use for it, but I'm just going to call it log. Well, anyway, I'm taking log of 1.5 now. And so I only did 4 intervals. And this isn't really all that tedious to do by hand. It may take you, if you don't even use multiplication on your calculator, this might take you 1 or 2 hours to do a good job at it. But you could get it done. And so what I got for that was, let's see, this here was 0.4055. And so here it is. And so if we get log of 3 by adding these two together, then that gave me 1.0986. And watch this, the actual, well, here it is. Okay, so look how much better of an approximation I got compared to this by doing stuff like change log of 3 into log of 2 plus log of 1.5. Okay, so let's do log of 230. And this is the actual answer. And I want to show a lot of things in the process of doing this. So really, if you tried to do the process we talked about with just 230, it would be an absolute nightmare. You'd have to have probably, I don't know how many rectangles, scores of them, and it wouldn't even be worth it. But what we can do is use properties of logarithms. So we know log of a times b times c equals log times a plus log, or sorry, log a plus log b plus log c. It's just a standard property of logs. And what I recommend that you do is figure out the logs of these primes, because you can go a long way with those, just those. And again, you're on the desert island. You're not even using a calculator for the division or multiplication. You're just doing this stuff by hand. And it's totally doable. So you you get these figured out, and then these are your tools for figuring out all the other logs. And you can go some more higher if you want, just do the prime numbers. Well, so rather than do 230, we're going to bust it up into, well, first of all, we're thinking of 230 times. What I did here is I factored 230 into 2 times 5 times 23. And then I used this property to rewrite it. And so now I already have this right here. What am I going to do with this? Well, that's prime. It's too big to really be convenient to work with, and I don't have it on the list here anyway. But what I did was I did 23 divided by 5, and so 5 times 4.6 is 23. So basically I just factored 23 into 5 times 4.6. Okay, so we're making progress. So I have this, this, and this. And so what about this? I mean, now this wouldn't have been horrible to work with, but we can still do a lot better, because remember, we want to keep delta x, really, my suggestion is no bigger than 0.25. And it's going to be bigger than that for this. Well, I just took 4.6 and divided by 2 and got 2.3. So I busted 4.6 up into these two. Now this would be totally doable. You could have just done this. But just for the heck of it, I went even further and I divided this by 2 and got this. And so this was the only thing that I had to figure out. I have all this other stuff. And so that's what I did here. I did log 1.15. Here's my work. You got to be careful if you get the right numbers here, but it's not hard once you do it a little bit. You're just using averages. So if you want to find the middle point between 1 and 1.15, do this plus this, divide it by 2, it'll give you this. And then to get this number, just same thing. Add this to this, divide by 2, it'll give you this, and so on. So it's not really as bad as it seems like it could have been. And then I just do Simpson's rule over here, and that's what all this is. And I used a calculator, of course, because I'm not going to work that hard. It's enough to know that I could do it. And I did one the other day just to make sure that, I had really done what I'm suggesting to you. Well, this is what I got, and the actual log of 115 is this. Well, it was really accurate because my delta x is really small. So you're going to get some good accuracy with a delta x that small. And so basically you have 0.6. All you have to do is add all these up now. See, log of 5, 1.6094, another one, 1.6094, 0.6921, another 0.6921, and then this here would be this, and I'll just leave it like that. And so what I got, so adding these up, that gave me 5.43786, and that is really close to the actual. And that's with a log of a pretty big number. So with this system, you can take logs of pretty much any number you want. One last example. First, though, I noticed on the last slide I copied the log of 2 wrong. It should have been 3.1 instead of 2.1. The total's still the same though, because I was copying, I was looking at something, and my total was really the same as if I had done this correctly. So I just wanted to correct that. All right, one last example here. So what about between 0 and 1? So we did log of 2, which is just a little over 1. Then we went way over 1, pretty big number. Well, now what about between 0 and 1? Um, so let's do log of 0.473. And now this would be the integral that, of course, we don't do, but we're approximating. But we'd be going from 0.473 to 1. But remember, we want the 1 on the bottom. So we're going to flip these, which means this has to be negative. And of course, logs between 0 and 1 are negative. So this is what it would look like when we do our sections. And basically, I don't need to say much. I just did all the same stuff. And this is what I got. And this is the actual. So that's actually pretty good. And you can always, like I've said before, be more accurate by doing more sections. So enough of that. So that's the enough for this video. I do want to give a heads up. I'm shortly going to be doing a video where we use what we've learned so far and extend it to actually be able to do this totally by hand. Normally this would be horrific under most circumstances. You need anti-logs, but then you have the same problem. We don't have log tables, but in the same way, we're finding a way around that with logarithms. We can do it with anti-logs, which means we can actually do this. I used to think that to do something like this, you'd have to convert it to a fraction and rewrite, as a root. And then, so, I haven't even figured this out, but you could have a horrific root to take on the outside here and a horrific power to do on the inside. It would just, it'd be horrible, but we don't have to do all that. So, hope you enjoyed this video.